So today we're going to talk about analysis of variance, or ANOVA, and then extend that to repeated measures ANOVA. So this is just a quick outline. As I mentioned, we'll talk about ANOVA and then repeated measures ANOVA. And then after that, we'll talk about planned comparisons and post-hoc tests that we typically would utilize after we conduct an ANOVA. So first, let's talk about ANOVA. So remember, we started off this class talking about how to characterize individual variables, right? So one way we can characterize, for example, a quantitative variable is by using the mean and standard deviation, or the median, interquartile range. And then we talked about a situation where we might want to compare the means for two groups. And that's when we talked about t-tests. So independent two-sample t-tests or paired t-tests in the case of dependent data. So now, what if we want to compare more than two groups? So if we find ourselves in a situation like this, we can use an analysis of variance as an overall test of the null hypothesis for more than two means. And what this does is it tests for differences among population means categorized by only one independent variable, and we call that variable a factor. And this is just an extension of the two independent samples t-test, and we call it an f-test. So again, it's similar to a t-test, but this time we can use it when we have a situation where we have more than two groups. So remember, t-tests are for two, so t for two, but if we have more than two groups, then we would use an f-test or ANOVA. So the F statistic for the f-test is just the variance between groups divided by the variance within groups. So the between group variation is the differences among the group means. So we're comparing the means for group 1, 2, and 3. The within group variation is just the deviations from the group means. So observations within group 1 compared to the group mean, and then we do the same thing for group 2 and group 3. And those are the within group that's the within group variation. And again, the null hypothesis for the f-test is that all the population means are equal, where k is the number of groups. So in this particular example where we have our population and we've drawn 3 samples from that population, our null hypothesis would be mu1 equals mu2 equals mu3. And if we had 10 groups, then that would just continue on up until mu10. And then the alternative hypothesis is that there is at least one difference between the means. But the f-test doesn't tell us which group is different. And so that's when we would then conduct additional tests. So why should we do the f-test at all? Why not just conduct multiple t-tests? So for example, we might do independent two-sample t-tests comparing A to B, A to C, A to D, and then B to C and B to D, and then finally C to D. The reason why we don't do this is that the more tests we conduct, the greater the probability of making a type 1 error or getting a false positive. So for example, if we conduct 20 t-tests at the alpha equals 0.05 level, then it's very likely we made at least one type error. Another reason is that the t-test doesn't make use of all available information about the population, right? It only looks at 2 groups at a time. And so if we were to do this, then there really wasn't much point in measuring the others, right? Then the final point is that if we conduct multiple t-tests, then it requires more calculations, right? Because now we're conducting a t-test for every pair that we're looking at. However, we can just conduct one single ANOVA or f-test to accomplish the same thing. Also, when we conduct multiple t-tests, we then need to adjust the alpha value. So there are a few assumptions for the ANOVA test. The first is that scores within groups are normally distributed, right? This is a very common theme. This is the same assumption as with regression. We also assume that there is homogeneity of variance, so the variance in the groups are equal. And we can test this using Levene's test. And if it's significant, then we can adjust the F test to correct for differences in variance using a number of different tests. We also assume that the data are independent. In other words, the data for different subjects do not depend on each other. And this was the same, right, for the independent two-sample t-test. Unlike with correlation or linear regression, there is no linearity assumption. And then just a quick note, if you do conduct an ANOVA test, you should try to keep the same sample sizes for each group, but it's not necessary. And that is one nice feature of this test. Okay, so remember, all groups need to be independent. The first thing that we do in analysis of variance is we partition the two sources of variance. So there's between group variance. So that's just the variability among scores of individuals who, being in different groups, receive different experimental treatments. And then we compare the group means to the grand mean. And then the second source of variance is everything else. It's the within group variance. It's just the variability among scores of subjects who, being in the same group, receive the same experimental treatments. And when we have independent scores, then any difference that we see here should really just be due to random error. And that could be sampling error, it could be measurement error, it could be researcher error, etc. So again, ANOVA is partitioned into two sources of variance. That's the between group variability and then the within group variability. And when we add that together, we just get the overall variance or the total variance. So in order to conduct ANOVA, we need the grand mean, and that's just the mean of all measurements or a weighted average of the individual sample means. We need the group mean, or the mean of measurements within each group, and then we need the individual scores. If we were to do ANOVA by hand, we would fill out what's called an ANOVA table. So this is just indicating the source of variance, and then the sum of squares corresponding to the variability for the between group versus within group. We would also need the degrees of freedom. We would need the mean square value, and I'll talk about these in a bit. And then finally, with all that, we can determine our F statistic, which we would then compare to our critical value to get our p-value. And then again, the within group variability, we're comparing individual scores to the group mean. For between group variability, we're comparing the group means to the grand mean. And this is just, the total is just the summation of those two components. So here's an example. Let's say we have 4 groups. So group is our factor, group 1, group 2, group 3, and group 4. And within each group, we have these measures. So we have 5 individuals in group 1, group 2, group 3, and group 4. And we want to know if there are differences between the means of the groups. So our null hypothesis would just be that all of the population means are equal. In this case, we have 4 groups, so it goes from mu1 through mu4. And then our alternative hypothesis is that at least one group is different. So this is what the total variance looks like visually. So these are our 4 groups. And the red line denotes the grand mean, so the mean for all of these values across all groups. And what we're doing is we're comparing these individual observations in each group to the grand mean. For the variance between, we're comparing each group mean, which is denoted by these heavy black bars, to the grand mean. And then the variance within, we're looking at the variance within each group, so the individual observations compared to the group mean. And then we do that for each group. So if we were to complete our ANOVA table, this is what it would look like. So I mentioned the mean square earlier, and that's just the sum of squares divided by the degrees of freedom for the corresponding source of variance. So the sum of squares for the between, variance between, divided by the degrees of freedom. And the degrees of freedom for the between group variance is just the number of groups, so K minus 1. And the degrees of freedom for the within group variance is the number of observations or the number of people overall minus the number of groups, and then the number of people minus 1 for the total degrees of freedom. Okay, so here's just an equation form, the mean square for between group variance, the mean square for within group variance. And then our F statistic is just the mean square for between divided by the mean square for within. So going back from our example, I calculated the sum of squares for between, within, and then this is the total. And remember, we had 4 groups, so the degrees of freedom is 3 in this case, right? K minus 1. Our degrees of freedom for within is N minus K, right, up here. So we had 20 individuals and there are 4 groups. So the degrees of freedom here is 16. And then the total degrees of freedom is N minus 1. So we had 20 individuals, so minus 1 is 19. And then we calculate the mean square. We get our F statistic. And if we use the computer to then calculate the p-value, we get 0.0188. So how would we interpret that p-value? So it's less than 0.05. Therefore, we would reject the null hypothesis in favor of the alternative. So remember, the null hypothesis is that all population means are equal, and the alternative is that at least one is different. So based on this result, we can say at least one of the groups is different from the other. And then this is just depicting ANOVA as a linear model. So remember, in our regression model that I showed last week, we just had y equals beta naught plus beta 1 x1, and it was just this. So in this case, we would just have more terms, additional terms, where x is just an indicator, so 0 or 1, where at most 1x equals 1, while we hold all others 0. So in our example, the model would be depicted here. So we had four groups, and then x1 is just an indicator for each x sub I would just be an indicator for each group. I'm sorry. X1 would just be an indicator for group 1, X2 would be an indicator for group 2, X3 would be an indicator for group 3, and X4 would be an indicator for group 4. So for example, for X1, as an indicator for group 1, then if an individual is in group 1, we would set this value to 1. And then if they are in any other group, so in groups 2, 3, 4, then we would set that value to 0. Okay, so now let's talk about repeated measures ANOVA. Repeated measures ANOVA is similar to a paired t-test, but again, just like the ANOVA comparing to an independent 2-sample t-test, the repeated measures ANOVA is analogous to a paired t-test, but now we're interested in comparing 3 or more groups. So this repeated measures design often involves measuring subjects at different points in time, or subjects measured under different experimental conditions. So in other words, we have multiple measurements on the same subjects. And I know some of you are doing some SURF research, and that is a great instance where we would want to use repeated measures ANOVA, where you're measuring, for example, temperature across time. So another example might be, we are interested in measuring individuals before, during, and after an exercise program. And then we have 3 different treatments. So we might be looking at endurance performance, listening to no music, preferred music, or non-preferred music. So we have these 3 different treatment groups, and we're measuring them across time. So before, during, and after an exercise program. As with our repeated measures t-tests, the repeated measures in an ANOVA should contain much less individual variability, right? Because it's within an individual. This is called a within subjects ANOVA because we can examine the effect of treatment within the same subjects. So we had similar assumptions as with the regular ANOVA. We have scores within groups are normally distributed. We also assume that there is homogeneity of variance. For repeated measures ANOVA, we have this additional assumption of sphericity. So that just means that the variances of the differences between all combinations of related groups or levels are equal. And we can test this using Moschli's test, where the null hypothesis is that the variances of the differences are equal. And then if this assumption is violated, then we can use various corrections depending on our results. So I wanted to give you sort of maybe a visual of what I mean by variances of the differences are all equal. So let's say we have 6 subjects and we're measuring them at time 1, time 2, and time 3. So then we take the difference between time 1 and time 2, time 1 and time 3, and then time 2 and time 3. And then we get the variance for each of those columns with the differences. And the assumption is that all of these variances are equal. And just kind of looking at this, it seems like maybe that's not the case. Okay, so again, we're partitioning the variance. For a one-way independent ANOVA, we had the between treatments and we had the within treatments. So it's similar for the repeated measures ANOVA. We have the between time trials, and that's the variability between time points or trials. We have the within subjects, that's the variability within an individual person's scores. And then we have the error or the unexplained variability, and that's corresponds to the within variability. So really the difference here is we have these, right, for the one-way ANOVA, but in addition now we have the within subjects variability. So our repeated measures ANOVA table looks similar. We had the between, we had within, but now we have this subjects row. And then again, if we were to add up all the variability, we get the total. And then similarly, we have the mean square, which is just the sum of squares divided by the degrees of freedom for each corresponding source of variance. And then these are just the equations for the degrees of freedom. Okay, and again, K is the number of groups and N is the number of individuals. And then our F statistic is the mean square for between divided by the mean square for within. And then we can get our p-value when we compare our F statistic to the critical value. Okay, so let's talk about planned comparisons versus post-hoc tests. So we can use planned comparisons when we have a set hypothesis or a priori we decide which tests will be conducted. So the basic idea is that the variability explained by the model is due to participants being assigned to different groups. And this variability, we can break it down to test specific hypotheses about which groups may or may not differ. And this is based on a priori hypotheses made before the experiment. So basically, we're deciding what comparisons we want to make before we conduct our experiment. Typically when we would use planned comparisons, it would be when we have a control group that we can compare all the other groups to. When we're making comparisons among only 2 groups, And then each group can only be used in one comparison. So let me give some examples. Sorry, let me just go over some rules and then I'll give you an example. So each comparison must test a unique hypothesis, and each comparison can only test two sources of variability or chunks of variation. And you will end up with K, so the number of group minus 1 comparisons. So here's an example. Let's say we want to test the effects of a drug on goals scored, and the goal scored is our dependent variable. So group 1 would be the placebo, group 2 would be low dose drug, and group 3 would be a high dosage of that drug. So what hypotheses might we decide to test before we actually conduct our experiment? So we might say for research hypothesis 1, that people who take the drug will score more goals than those who do not take the drug. So here we're comparing our placebo versus groups 2 and 3. So people who take the drug, whether they're low dose or high dose. And then another research hypothesis might be that people who take a high dose of the drug will score more goals than those who take a low dose of the drug. So comparing group 3 and 2. And notice there are other possible comparisons, right? We can compare the placebo to the low dose only or placebo to the high dose only, but we're deciding a priori not to do that. If we don't have planned comparisons ahead of time, then we would be conducting what is called a post-hoc test. So this is when we don't have any set of hypotheses when we first set out to conduct our experiment, and then we basically run tests after the fact once we get our result from the F-test. So remember, when we get a significant F-test result in an ANOVA, this tells us that we can reject the null hypothesis. In other words, the samples are not all from populations with the same mean, but we don't know which group is different. And so that's where we would use post-hoc tests, and those can tell us which groups differ from the rest. There are many, many different types of, many different post-hoc tests, and they all make different assumptions about equality of variance, group sizes, and they all compare each mean against all others. In general terms, they use a stricter criterion to accept an effect as significant. And so they all control for the family-wise error rate. So these are just recommendations for post-hoc tests. If test assumptions are met, we can use the Reg WQ or Tukey test. Another option, it's a very conservative option, is the Bonferroni test. I'm sorry, the Bonferroni correction. If we have unequal sample sizes, we can use Gabriel's test for small sample size or Hochberg's GT2 for large sample sizes. If we have unequal variances, we can use Games-Howell. If we had to conduct many, many tests overall, then we might use the Benjamin-Hochberg procedure. And then if we have a control group, then we might choose to use Dunnett's correction. And then I'll talk about some of these in a little bit more detail. So I mentioned the family-wise error rate up above, and that's just the probability of coming to at least one false conclusion or making at least one type error within the family of tests under consideration. This is also called alpha inflation, so it's the cumulative type 1 error. Okay, so the first correction post-hoc test, or it's really more of a correction, is the Bonferroni method. So in this case, we would divide the alpha by the number of comparisons to be made. So typically our alpha level is set to 0.05. And let's just say we're making 10 different comparisons. So our new alpha, our new cutoff for the p-value would be 0.05 divided by 10. So in this case, it would now be 0.005. So for example, if we were to perform multiple t-tests, then we would use this new alpha, 0.005, as our level of significance. And you can see that if we, for example, have many, many different comparisons, and this is actually the case in a lot of genome-wide association studies where we're making thousands of comparisons, this new alpha level can become very, 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 very small. And this is what we mean by it's a very conservative test. And so we might actually miss truly significant results. So again, the Bonferroni is often considered too conservative. So alternative procedures have been developed. So one is the home Bonferroni test. And the equation for that is just the target alpha level, and that's usually 0.05. And then it's divided by n minus the ranked number of pair plus 1. So let's say we have 10 different tests, all with their p-values, and what we would do is rank the p-values from smallest to largest, and then we would calculate the HB value using this equation, and we would do that for each test, and then we would compare each p-value to the HB value. And then the testing would stop once we reach the first non-rejected hypothesis. Another post-hoc test is Fisher's least significant difference. So this is a tool to identify which pairs of means are statistically different. So the LSD calculates the smallest significant difference between two means as though a test had been run on those two means, as opposed to all groups together. And this enables us to make direct comparisons between two means from two individual groups. And then if any difference larger than the LSD, we would then consider that a significant result. Fisher's LSD has been criticized for not sufficiently controlling type 1 error. So another test is Tukey's test, and this is probably one of the most widely used. The purpose of Tukey's test, again, is to figure out which groups in your sample differ. It uses what's called the honest significant difference, which is a number that represents the distance between groups to compare every mean with every other mean. And it calculates this new critical value that is used to evaluate any two pairs of means. It generally has more power than other tests, but if not all comparisons are needed, then we might choose to conduct another post-hoc test. So another test is the Ryan Eleanor Gabriel Walsh test. It's a procedure that is similar to Tukey's test, and it does demonstrate good power and tight type 1 error control, but it's a complex procedure to calculate. Another correction is Dunnett's correction. So like Tukey's, Dunnett's correction is used to compare means. But unlike Tukey's, it compares every mean to a control mean. So it can only be used when we have a control group. Otherwise, we should use Tukey's test instead. And it works similar to a t-test. There's also Games-Howell, and that's similar to Tukey's test, but it does not assume equal variances and sample sizes. It uses ranked variables for non-parametric data, and that's also a common theme. When we have non-parametric data, we usually use some form of ranking the scores first and then making comparisons. This test does do better than Tukey's test if the variances are unequal, or if there's a combination of moderately unequal with small sample sizes, or if we have very, very small sample size within each group, or fewer than 6 people. We also have the Benjamin-Hochberg procedure. So when we're running a very large number of tests, remember one or more of the tests will have a significant result purely by chance alone. The BH procedure accounts for the false discovery rate. And the false discovery rate, let's say we set it to 5%, it just means that among all tests that we designate as significant, 5% of these are truly null. And we can actually set the false discovery rate. That's something that the investigator sets, but it is typically set at the alpha level. So here's what we would do for that. So we would put individual p-values in ascending order, and then we would assign ranks to the p-value. So the smallest has a rank of 1, the next has a rank of 2, and so on. Then we would calculate the individual p-values, we would calculate each individual p-value's Benjamin Hochberg critical value, and we use this formula I divided by n multiplied by q. I is just the individual p-values rank, m is the total number of tests, and q is the false discovery rate. And again, it's typically set at alpha. And then we would compare our original p-values to the critical BH and find the largest p-value that is smaller than the critical value. And then everything above that is significant. So this is what it looks like. This is just a snippet. It just shows 8 different tests, but there's actually a long list of 25 tests. And then we would just rank the p-values in ascending order. And then we calculate the Benjamin Hochberg critical value, and that's just indicated in this column here. And so then we would calculate the p-value to the critical value for each p-value. And then once we reach this point where this is the last p-value that's smaller than the critical Benjamin Hochberg critical value, that's where we would stop. And so all of these would be considered significant, and then everything below it would be considered non-significant. Finally, there's Sheffy's method, and that is used to determine which pairs are significant. And Sheffy's method controls for the overall confidence level for differences, and we generally use this for unequal sample sizes. This corrects the alpha for simple as well as complex mean comparisons. And what I mean by that is that they involve comparing more than one pair of means simultaneously. So it has lower statistical power than other tests, but it is the most flexible. If we just want to do pairwise comparisons, then Tukey procedure is often better. But if we want to make complex comparisons, then Sheffy's test is better. So I know there's a lot of different tests that we talked about, post-hoc tests, but we will conduct some of these in the exercise. So hopefully once we do that, it'll help solidify everything. And I'll also go through a quick recap of ANOVA and repeated measures ANOVA at the start of live lecture 5 as well.